Okay. The next statistical test that we're going to do, and this again, it's for biological statistics. We do this whenever we're doing population samples or maybe samples of some kind of abiotic factor. And this one we'll be looking at microplastics. Um, all right, so this is going to be the chi-squared test, and it's noted with this x squared, that x is chi, or lowercase. All right, so from just to recap, first one we did was standard deviation. If you're deviating, you're moving away from something. So this was how spread the data is around the mean. So on average, how far are the values on average compared to the mean, or where the average is. Standard error was just the last one that I did a video for and went over. Here you'll use your standard deviation. Remember, in the alphabet, T comes before E. So you have to do the deviation before the error, but that would be evident in the formula because the standard error formula requires the deviation. So here we're going to use the standard deviation to measure how accurate the population size is from the actual population size. All right, and then we looked at that with a confidence interval of 95%. So we would say with a 95% accuracy, we could identify what the range of the actual mean was. And we would compare that to what we actually calculated, and then be able to either accept our null hypothesis or reject our null hypothesis. Okay, so the chi-square test going to look like this. Just the formula for it. Again, you will be given the formula on this, on any of these, and you'll be given what the variables mean. There is, yes, okay, so this part number 8, you can see like I accentuated the border lines here. I made it much thicker than the rest. This, for the degrees of freedom, that will be one that you will have to know, but it's just a number -1. That's it. But I'll come to that. All right, so in this example, we're going to use the data below. So looking at 2 different shoreline locations and then the amount of microplastics that are found in a square meter quadrat. All right, so the North Inlet has 376. South Inlet is going to have 340 on average. And so we want to see that if there is like any significance between the expected versus the observed amount of microplastics there. And if they're actually that different from each other. Okay. So the first step. So you can see that the North Inlet does have more microplastics than the South, but are the differences actually that significant? Like, we see the average here. These are your averages, but is it, we can visually identify 340 versus 376. North Inlet's definitely got it. But when we actually start looking into those numbers, are they much more different from each other? Or maybe is there some overlap in the means? Okay, first thing you're going to do is create your null hypothesis, which is actually one of the questions on paper 3. I'm sorry, not paper 3, it's paper 4. That example covers the Spearman's ring value, which I'll do a video for as well. So the null hypothesis is actually called like the not hypothesis, the null or the not. And essentially, you will always say for the null hypothesis that there is no difference, or you will expect there to be no difference between your 2 variables. And so what we're looking at is location. So north of the inlet and then south of the inlet. So our null hypothesis is going to say, for this specifically, there is no difference in the number of microplastics found between the north inlet and the south inlet. That is the null or the not hypothesis. The opposite of this is referred to as the alternative hypothesis. I'll write that in there. It's called the alternative hypothesis. And essentially, it's going to say the alternative of your null hypothesis. If the null hypothesis, it's always going to say something along the lines of there is no expected difference between the categories. And then obviously you'll specify more with like what the categories actually are. But then the alternative hypothesis is the opposite. So there is a difference between the categories, or there will be a difference in the number of microplastics in different shoreline locations. So it's going to be step one. All right, you will be given a table, but in this one, I just kept adding to it and just duplicated that same table. But other ways that you'll see it is you just have one table provided for you, and you'll just, in that one table, just add in your values as you do them. But I just wanted to like take it step by step. So you'll set up the chi-square table. You're going to add the observed data, and that's what's given to you. Here is your observed data. North inlet, you had 376, the south inlet, 340. All right, now in the words. In the formula, this is it right here. It's the O, the observed. And this is from your data provided, so you'll fill that in. Okay, that's step 2 done. It's done for you. And you will be provided this table. You don't need to know how to fill it in, but you know, the ease of this is that you're given the formula, you're going to be given what each variable means. So it's just to your benefit to just go through these and just practice them in case this is one that you see. Now in the chi-squared, you won't have to do, and it says this on the syllabus, you will not have to do every single column or row in the table, but you might have to do one, whether it be a row or a column of the table. All right, so to find the expected. The expected column is for data that would be expected if your null hypothesis is true. Our null hypothesis says that there is no difference in the number of microplastics found between the north and the south inlet. Well, if there's no difference, then that means they would be the same. There would be a same amount. So you might be thinking, well, then which one do I go with? Do I go with the 376 or go with the 340? Like, well, you can't really make that decision. So instead, we will take their average. And on our formula, it's this right here. It's the ease. So expected column is for data, again, that would be true if your null hypothesis was true. So essentially that there's no difference between the categories. The amount of microplastics found on each shoreline is the same. If there is no difference, then their values would be the same. Right, and this, again, is just an example for microplastics, but I mean, what if it was about temperature of water and the amount of operculum movements in a minute? Well, then you would say, like, if that was it, then your null hypothesis would say there is no difference between the temperature of water and the amount of operculum movements. Okay, so to find this value, we're going to calculate the average of your observed data to essentially like share them equally. So data 1 plus data 2 divided by 2. And so the data we have North Inlet, which is our first set of data. And the second one is 340 divided by 2. All right, so if you add those up and then divide it by 2, you'll find that the expected value then, if you do their average, is going to be 358. All right, and so that's what E is going to equal now. Okay, add this to your chi-squared table. All right. The next step then is going to be this part, the O minus the E. So subtract your observed values that are given in the data table. They were given right here. You will be given the observed value from the expected value that you just calculated in number 3, the last step. So you'll have 376, which is the observed value in the north inlet. And we'll take it from 358. Same for the south inlet, 340 from 358. Also, side note, if you printed this out prior to me doing this, then you may have a typo on it. When I was making this, I did just like copy and paste like this same format right here. So your paper might say for the south inlet 376. So make sure that you change that. It is 340. That's my B, but I did fix it now. So if you do look on your Google Classroom and look at it, it should have the corrected value of 340. Okay, now if you do those subtractions, 376 minus 358, you're going to get 18. 340 minus 358, you'll get negative 18. All right, add those to your data table. Again, the chi-square table will be done for you. And if you notice, just for ease of it, I do put in the next sequential data tables, the data that you have already calculated. So you don't have to just fill them in, all of them right away. Because in a real situation, they would just give you one table to be filling in. All right, if you can see in the formula then, the next thing that we're going to have after we do the subtraction is we're going to square it. Okay, so square each difference from the observed from the expected result that you just did in number 4. All right, so in the north inlet, observed minus expected, 18 squared. And in the south inlet, negative 18 squared. You're going to add these to your chi-squared table. Go ahead and do those. I know even though they're done for you, it's just good practice. It's easy enough that you should be able to follow along. And it's split up enough that you should be able to follow along. So I would at least make sure that you're getting those values correct. If not, you might just be making like a simple calculated error. Okay, so you should get 18 times 18, 324. And then a negative 18 times a negative 18 is also going to be 324. All right. I got them in there for you already. All right, almost done with this formula. It's a couple more steps. Now we're going to divide the squared difference that you just did in number 5, right there. We did the difference, observed minus expected, and then squared it. Divide the squared difference from the expected value from number 3. And to get the expected value, again, we added up both of the observed and then divided by 2, just to get their average. Because the expected value is what would you expect if there was no significant difference between the data set, or specifically the microplastics in the north and the south inlet. All right, so observed minus expected in the north inlet squared is 324. All right, and we're going to divide it by the expected. That's 358. And it just so happens in this example, they're going to be the same. And then the south inlet, 324. All over 358. Okay. All right, and you should get for your answer 0.905, 0.905. Okay, last step then. Finally, we're going to take the summation, the total of your quotients from number 6, what you just divided in number 6. So add both of the values that were calculated in 6 together, their summation. So this part we already did, and now we're just going to add them. Okay, so north inlet, 0.905, the south inlet, 0.905. All right, and you're going to get, come on now, 1.810. That is your chi-squared value, which right now, that might not mean anything to you. And honestly, it really won't until you correlate it with a data table that has already been given to you. It is like a standard table for chi-squared calculations, and it will always be given to you. Always, 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 always. It's always given to you. But you're going to have to be able to get this number so that you can actually compare it against what is already going to be a standard in mathematics. All right, so number 8, now that you have the chi-squared results, you can start to determine if there is actually a significant difference in the microplastic values. It did look like there was, with the north inlet being 376, the south 340, but we, just because those numbers we can tell are different from each other, that, like, is it actually that significant? So this is where we're going to need to look at degrees of freedom on a chi-squared table, or critical values on a chi-squared table, but right now we'll just look at DF, or degrees of freedom. All right, and we're going to do this, reason is so we can determine if there's a significant difference in your microplastic values on the beaches, or anything you need to compare. Again, if it's operculum movement in different temperatures, or if it's the rate of oxygen produced through photosynthesis at different wavelengths, you would use this same method to see, like, okay, I can tell if there's a difference, but is it actually significant? All right, so you'll need to find the degrees of freedom. And this is something, even though I said you don't have to know any of them, not to overwhelm you, this is the one you will have to know. So if they say calculate your degrees of freedom, here's how you do it. And just this definition, real quick. These are the amount of values that your final calculation is allowed to vary, or like allowed to be wrong without saying your data like doesn't really qualify, or like your data isn't enough. And if that's the case, you just need to take more samples. But yeah, so degrees of freedom literally is like the value freedom, like how much freedom does it have to actually vary before you're like, yeah, actually your data's trash. Or like your data doesn't really have anything that can be, significant about there being a difference. Okay, to calculate degrees of freedom, you're going to take the amount of categories that you had. We had 2 categories. We had the North Shore, and then we also looked at the South Shore. And you're going to take that minus 1. So degrees of freedom equals categories minus 1. DF cat minus 1. DF cat minus 1. Or DFC minus 1. Okay, and so you have to know this. So even if it was operculum movement by species, right? And they looked at 3 different species of fish. Then we're going to say, and maybe they kept it at the same temperature. It's going to be at 20 degrees Celsius. We're looking at 3 different species of fish. Then 3 is going to be your category, and you'll subtract from 1. Your degrees of freedom would be 2. In this situation, we had 2 categories minus 1, so our degrees of freedom is 1. All right. Now, you will be given a chart very similar to this. You will be provided it. This is the last step. So we have the amount that we know that our data is allowed to vary. That's the degrees of freedom. It's 1. We also have our chi-squared results. So these are the things we want to consider. Our chi-squared result is 1.810, And on our critical value chart for chi-squared, our degrees of freedom is 1. Okay, so the last step, you will be provided this. Nobody memorizes these. And you're going to correlate the degrees of freedom, which is 1. It's the amount of categories you have, -1. It's always going to be -1. To your critical value, P. P stands for probability. We will only be looking at a p-value of 0.05. Now, I imagine they will tell you, like, calculate it for a value of 0.75, but if not, that has been the standard. That's also what we did with the confidence interval. We looked at for confidence interval for standard error. We looked at a confidence interval, the same of P05, or that we're confident that 95% of this data was going to lie, with this range of the mean. In this one, we're also going to be using the same type of confidence interval, and that's what p-value stands for. P-value stands for the probability value. So there's 5% probability that in this one that our data is not significant. But 5%, the other remaining portion of that is 95%. So then otherwise we're 95% confident that these values will be significant or not significant. It really just, we need to actually look at the table to see how these numbers will end up working out. But that's what the p-value stands for. It stands for probability. Okay, so over here, you can see that there is a degree of freedom chart. And then across the top, you have your different p-values. All right, and again, we are just using that 0.05. 0.05 is pretty standard. Depending on the data collection that you have, there is times you would use other ones, but that is something for when you go to like a university and if you're in like higher level biological statistics. Nothing we need to concern ourselves with now. All right, this one. So we're at a p-value of 1. Yes. Bring out the ruler. Y'all, I'm so pleased with that. I'm just so pleased with it so much. And then just the 5%. So that really saying like there is a chance. There's a 5% chance that our data is wrong, but that 95 sounds good to me. All right, and so it's, oh, I built in that red. Silly me. The red came with it. Okay. So this is the, y'all. All right, this is the p-value. 3.84. So for a degree of freedom 1, we got that because we had 2 categories, and then you subtract 1. That's it. How many categories minus 1? And then we're looking at it at 0.05 p-value, like p-value critical value, probability value. We're always going to be doing that 0.05. That won't change. So 3.84 is what the chi-squared says that your value is allowed to deviate at. Well, and I gave you, and remember back, our value that we calculated was 1.810. So that's literally how much our values that we calculated, that's what our calculated values deviated from. And the standard, this is like the standard right here, says at that degree of freedom with 5% probability, values are allowed to deviate up to 3.84. And we got it at 1.81. So essentially it's going to mean our values are pretty good. And there is a significant difference. But spoiler alert there, I won't do it yet. All right, so what does a p-value of 0.05 mean? This means the critical value for 1 degree of freedom, the p-value of 0.05, that there's a probability of less than 5% that the differences in microplastics on the shoreline are due to chance. So like yeah, they can be significantly different from each other. However, that was random and that could have happened, anytime. It's not certain, and you won't see that trend again. That's not too common. Less than 5%, that means you're greater than 95% confidence. So what does this mean for your data? If the critical value that we calculated, which we did, is 1.81, is greater than the critical value for P in the chart, then we will reject the null hypothesis. Oh, sorry. So saying that there is a significant difference between the microplastics on the shoreline. If our calculated critical value is less than the critical value for P, we will accept the null hypothesis and say that there is no significant difference between the microplastics found on the shoreline. And I misspoke. There won't be a significant difference. Okay, so let me read that again. If the critical value that we calculated, 1.810, is greater, which it is not, then the critical value from the P chart, then we can reject the null hypothesis and then ultimately accept the alternative. If we're rejecting the null hypothesis says that there is not a difference between the amount of microplastics on different shorelines, and we're rejecting it. If we're rejecting that, then we're saying that there actually is a significance between the microplastics on the shoreline. And that's if our value is greater than that critical value. If our calculated critical value is less than the critical value for P, which it is, we will accept our null hypothesis and state that there is no significant difference between the microplastics found on the two shorelines. And so it's going to take into account, like, what was it, 376 and 340? We can look at that and see that there is a difference. There's a difference of 36, but like compared to the entirety of the data, 376, 340, how significant are those values from each other, or how different are they from each other? And so our value was less than the value allowed on the P chart here. This is when we're at. So there is no significant difference between the microplastics found on the shoreline. We can see that their average is different, but perhaps maybe if you took more averages, did more samples, those values might start to straighten themselves out a little bit. So therefore, there is a probability that 5% of the difference is due to chance. And again, full admittal there. I prior to getting down here, I did misspeak. And here's ours. In our example, the p-value is 3.81 or 3.841. Even though you only see to the hundredths place. The calculated critical value that we did is 1.81, and we did that right here. This is not greater than the critical value on the chart. So if we had a value that was like 3.85, pretty close, but still it's going to be greater than that p-value. The one we calculated, 1.81, is not greater than the critical value in the chart, so we are not going to reject the null hypothesis. Instead, we will accept it. And so by doing that, we're saying that there is no significant difference between the microplastics on both beaches. All right, and so you're looking to see if your value, this is the calculated value, if it's greater than what you have on the chart. So the calculated value, if it's greater than what's on the chart, then you can reject. the null hypothesis. But if it's less than, then we will accept. Accept the null hypothesis that there is no difference. Okay, great. Remember, you don't have to memorize these at all. You will have to figure out the different degrees of freedom. And that is just your number of categories. And in this case, we had two. If we looked at 5 different shoreline areas, then we'd be doing 5 minus 1 for the degrees of freedom. And then our degrees of freedom would be 4. If there was 12 different shorelines we looked at, then we would do 12 minus 1. The degrees of freedom would be 11.